Hello, this is Mr. Stansbury. I'm going to take you through the notes on optimization. At the end of this, you should be able to say, I can find the optimal value for a variable in various real-life situations. Okay, so first thing, optimization. Optimization is finding the maximum or minimum of a function to find the best solution. Or another way to say that is to find the optimal solution, hence the word optimization. Okay, so for example 3, square corners are cut from a 15-inch by 26-inch piece of cardboard, which is then folded into the shape of a box with no top. What size squares should be removed to produce the box of maximum volume? Okay, so if you'll remember, volume is length times width times height. Right, so we want to come up with the volume, the biggest volume we can make from this hunk of cardboard here. So just so we can kind of get an idea of what we're looking at here, let's draw our cardboard box. We got 15 by 26. Okay, and then so what we're going to end up doing is we're going to cut these corners out of this box. Right, and then we're going to end up folding those. After we cut these corners out, then we'll end up folding up the remaining parts to make a box. So basically, if those were the corners that we cut out, then we would end up folding it up right along these dotted lines here, and we would end up making ourselves a nice box. Okay. And again, we want to try to get the maximum amount of volume out of this box. So we know that this length here is say 26 inches, and this here is 15 inches. And it says we are going to cut square corners out of each corner of the box. So let's call each of those dimensions there would be x, and since they're square, it's going to be x by x, right? Okay, so we get x by x on all those corners. So basically, this length right here is going to be the 15 inches minus these two x's here. So this inside piece here is going to be 15 minus 2x, because again, from here to here is 15, and we subtract off those two x's to make this length right here. And then this dotted line from here to here is going to be 26 minus 2x. Okay? So, hopefully from that, we can now figure out what our dimensions are for our box should be. So volume is going to be, let's call length this way. So again, once we fold this up, we'll have a box, and we'll call the length 26 minus 2x. And then we'll call the the width, say this here, 15 minus 2x. Okay, and then the height, when you fold these all up, the height is just going to be this x, because we're going to basically take this flap here and we're going to fold it up, so now it's going to be x units high, so all times x. So there's our length, our width, and our height. Okay, so what we're trying to do is we are now trying to find the maximum volume of this here. Now, there's a couple ways we can do this. We can go through and we can actually we can multiply this all out, and then we can find the derivative, and then what you'd want to do, because basically this here is going to make like this, something like this, and we're looking for that maximum point right there, right? It's going to end up with some kind of function going on like this, and we're looking for that maximum height. Okay, so again, we can go through and do the derivative and find it all that way, or we can do it on the graphing calculator. So here's what I'm going to do. I'm going to actually go through and show you how to do this by hand, and I'm going to suggest just watch and kind of understand, and then I'm going to show you how to do it on the graphing calculator, which is significantly faster and easier. But I want you to at least understand what the heck we're doing, okay? Okay, so here's all the work by doing it by hand. So I'm just going to run you through this really quick. just so you can see what you're missing by doing it with the graphing calculator. Anyway, so we've got volume is length times width times height. The length 26 minus 2x, width 15 minus 2x, height x. Okay, so multiplying these out, so foiling these two or multiplying these two here, we get this. Still have the times x. Just collected these two like terms to get this here, and then I distributed the x to all of those and then reordered it as well. So I put 4x cubed first minus 82x squared plus 390x. Okay, now what we want to do, that's the function. So what we want to do is we want to find the maximum, we know that the tangent to the derivative will have to have a slope of 0 when it's at its maximum or if it's at its minimum point. Okay, so what we did is we took the derivative of this, ended up with that, and we set it equal to 0. Now we have this 12x squared minus 164x plus 390, so you could try to factor it. It won't factor, but instead plugged it into the quadratic, figured all this out, and came up with our answer of 10.60 or 3.07. Okay, now if we cut out corners of 10.6 on a 15-inch side, 10.6 and 10.6 this way, that's more than 15 inches, so that can't even work. So it would have to end up being 3.07. Now, that's doable. We can do that, but we can save ourselves a whole bunch of time by actually doing this on the graphing calculator, and that's what I'm going to show you here. Okay, so what we're going to do is we are going to just go into the y equals, and we're going to just enter in this right here. We're going to put that into our y equals, and we're going to basically just graph this thing, and we're going to find the maximum. That's going to take place of all this other stuff that we had to do here. So we've got 26 minus 2x times 15 minus 2x all times x. Okay, now if you go to graph that thing on the regular old window here, you're just going to get this blue line that goes straight up, and you won't be able to see anything else. Okay, so what we have to do is we have to change our window. So obviously this thing goes way up here and then it comes way back down. So like x, we're actually fine with the x's. We just need to see way farther up on the y. So what we have to do is go into window, and right now our y maximum is 10. So again, that thing looks like it went way up there. So I'm gonna just try 1,000. Okay, you could try 100 and see if that works. I'm just going to try something big and see if that works. And then when I go to push graph, it's going to eventually show up. It's being a little slow here, but there it goes. So it goes through and it graphs this thing, and we want to find this maximum point there. So all we have to do is do second trace, which is calculate, and we're going to find the maximum, which is 4, right? So now we just get this thing, oops, there it is. Sorry, it's acting a little slow right now. But so we get this thing to the left of the maximum, push enter, just like we've done before, and then we're going to get this thing to the right of the maximum, and then push enter again, right? That's definitely to the right of the maximum, push enter. And we'll get these two little arrows up here. It's going to say it's going to find the maximum y value between those 2 points. We push enter one more time because it's asking us to guess. So we push yes, and we get, guess what we get? 3.065, which rounds to 3.07, which is right there. And the nice part about this is actually tells us what the maximum volume would be. They didn't ask us for it, but yeah, they just said what size square should be cut out. So we should cut out 3.07. Are these by inches? Yeah, inches by 3.07 inches to maximize the volume on this box here. And again, that volume would be 540.2 cubic inches. Okay? So you're welcome to do it this way with all the math there, or you can just put this into your graphing calculator and find the maximum, because that's really what we were doing anyway. Okay? All right, I'm going to end this video here. So if you have any further questions, please feel free to ask in class. And then I'm also going to include another video that has just a few more, at least one more example with optimization in case you want to see some different ones. Okay? Okay, thanks.